All right, welcome to part 4 of 1.1 functions. We're going to be going over something called the difference quotient. This is something we'll kind of go over a few different times throughout the year. The difference quotient is a measure of the average rate of change or slope over an interval. Now, slope, you may remember, is in reference to the graph of lines, right? It's how tilted those lines are. Positive, it's going up. Negative, it's going down, right? The bigger the number, the more steeply it's increasing. Well, technically, we can talk about slope on a curved graph as well. So we can talk about it over a large interval, right? We can kind of connect 2 points here. So if we wanted to talk about the slope of this parabola on this interval from right down here all the way up to here, right? We could just kind of draw in a line between those values and calculate the slope of that line. And that would be the average rate of change. It's changing a little slower than that line in the beginning, but then a little faster, a little steeper at the end. And this line just represents the average rate of change on this interval. So, right, this would be a length of 4 and then a length of 8. So this line actually has a slope of 2. Up 2 over 1, up 2 over 1, up 2 over 1. So the average rate of change of this function over this interval happens to be 2. Now, that's interesting in some respects, but what becomes a little bit more interesting is as we start to make this interval smaller and smaller and smaller. So if I clear everything I've got here, and let's say we look at a much smaller interval, so only from here to, I don't know, here, and we connect that with a line, right? Notice how close, well, I didn't draw a very good line, but notice how close that line is to our graph and the actual curve of the graph. And so the smaller and smaller an interval we look at this on, this actually approaches the slope of our curved graph. And that's where it starts to get interesting. We actually want to look at the limit of this as h approaches 0, h being the length of our interval. Now, we're not going to do that right now. That's something to look at in the future. But as that interval gets smaller and smaller, what we come up with is we actually come up with the instantaneous rate of change of our graph at any given point on there. And we can actually calculate that. It becomes a formula. That's something you're going to study in your next course, in a calculus course. That's kind of one of the first things you start looking at is the instantaneous rate of change of these curved graphs. It's referenced as the derivative of that graph. And the derivative has tons of applications and is a very, very useful thing. So what we're doing is sort of preparing that concept by looking at this calculation, this difference quotient calculation, which is so important. All right. Let's go ahead and do that. So we're going to calculate the difference quotient for this function. Technically, it's not written in function notation, but let's just go ahead and fix that. F of x is equal to negative 4x plus 1. Well, you may be saying, this is a line. If this is going to calculate average rate of change, isn't this just going to give us the slope of our line? You would be right, but let's actually take a look and show that that happens. So our difference quotient is f of x plus h. We put x plus h into our function, do that, minus the original function f of x. So f of x plus h is negative 4 times x plus h plus 1, right? Replacing x with the expression x plus h. That's what I did right here. Minus our entire original function f of x. So negative 4x plus 1 all over h. So there we go. We got to do a little bit of algebra here to kind of simplify this down, but hopefully we'll see how this does indeed simplify down quite a bit for us. To make things a little simpler, the denominator is just h. That's not going to change. I'm just going to work on simplifying this numerator, and then I'll kind of bring it all back together in just a moment. So we'll distribute this. We get negative 4x minus 4h plus 1. Distribute this minus here, so it becomes plus 4x minus 1. All right, let's go ahead and do some calculations. We have negative 4x and positive 4x. Those cancel nicely. We have negative 4h. There's nothing for that to happen with. And then we have a 1 and a negative 1. So actually, those are going to become 0 as well. So the entire numerator simplifies to be negative 4h, all over h, right? It was all over h. Well, now there's even further simplifying that can happen, and we end up with simply negative 4. Kind of cool. That was the slope of this line. This line had a slope of negative 4. So if we kind of look at kind of a visual image of this, you remember that the difference quotient is calculating the average rate of change or slope of the graph over an interval. Well, this graph is always going to have a slope starting here at 1. That's our y-intercept of down 4 over 1, right? Down 4 over 1. That's the slope of this line. Slope of this line. So no matter how big of an interval we look at, whether it's, you know, a huge interval or a really, really small one, the slope's going to be the same as the slope of the line, which is negative 4. Anyway, the important part about this is right up here. It's simplifying this difference quotient down, being able to evaluate f of x plus h, and being able to simplify that down algebraically. This was a pretty easy equation, a simple linear equation, so not too complicated there. As the function itself becomes more and more complicated, this simplifying process will also become more complicated. So we'll go ahead and look at another example. All right. Did I accidentally go through? No. All right. So here's our function now. We have a quadratic function, not terribly complicated quadratic, but it is a quadratic. We have x squared there. And we're going to simplify that difference quotient again. So we need to figure out what f of x plus h is. Remember, again, that's replacing x with x plus h. So it's not too difficult there. It's x plus h squared plus 2, right? We just simply replace this x with x plus h. Now, that is more complicated because I have to square that. I actually have to multiply out x plus h times itself. Luckily, it's pretty easy to do this, right? You know, we're just distributing twice or foiling or whatever we need to do. We're going to end up with negative 3 times x squared plus 2xh plus h squared plus 2. All right, so that's our f of x plus h. And now we're subtracting away minus the whole original function f of x. So this is our original function f of x. And all of that is being divided by h. So you can see there's still quite a bit to do up here in the numerator. We have some distributing. There's probably going to be some things that are going to cancel out or simplify. So let's go ahead and carry that through. Distribute this negative 3 into that quadratic right there. So we have negative 3x squared, negative 3 times here, it's going to be minus 6xh, negative 3 times h squared is minus 3h squared. Okay. Plus 2, nothing going on there. And then distribute this subtraction in here. So minus minus becomes plus 3x squared, minus plus, it becomes minus 2. Again, we're always going to find some stuff cancels out here when we're simplifying the difference quotient. So if nothing's canceling out, you got to take a look at your process and find a mistake, because there should be things that will simplify down and cancel out. All right, we have 3x squared, negative 3x squared. Those are going to go away. We have plus 2 minus 2. Those are going to also cancel out. And let's just leave it right here. We have these two values. Nothing, those can't go together. Those are not like terms. So let's go ahead and write those down. We have negative 6xh minus 3h squared. Now, keep in mind, this was only the numerator, so we are all over h, right? That denominator of h didn't go anywhere. I just was kind of leaving it out for a moment to do all that simplifying. Well, we can distribute this division of h to cancel out some of these h's because, well, each term in the numerator has an h. So that one will go away, and then one of these will go away. So this will further simplify down to be negative 6x minus 3h. And that's our difference quotient. That is as simple as this can get. Now again, remember, this is kind of an advanced technique, but what we will eventually be looking at is we'll be looking at the limit as h approaches 0. So what happens as h gets closer and closer and closer to 0? And so after all, you can't just plug 0 in here because that's a problem. Dividing by 0 is a problem, not allowed. However, after you've done all this sort of fancy simplifying, you can plug in a 0 here and see what happens and see that you get this. But that's a little more advanced. We would actually just be okay with this whole thing, negative 6x minus 3h at this point. That's what we want to have simplified down. Anyway. All righty. And that's it for part 4. See you guys later.